To start with a quick outline, I'll do a very brief overview of the cement manufacturing process and where the two units, the calciner and the conditioning tower, fit in the overall process. And then I'll jump into the Barracuda model of the calciner, spend a lot of time there, and then finally I'll end with a conditioning tower model. And then I have some nice images here, just to again fill up the white space and to set the tone for the presentation. To start with a quick overview of the cement manufacturing process, I have a schematic here. So cement manufacturing is a high temperature pyro-processing operation in which raw materials such as limestone and clay are converted into cement clinker, which is then finally ground into cement powder as we know it. And this schematic shows the entire flow. Here there's several key stages involved. So we have the preheating of the raw material. In the preheater stage cyclone, essentially the finely grounded raw meal is dropped into the top stage cyclone, and then it flows down and it exchanges heat with the gases flowing upwards. And then the preheated and the partially calcined raw meal is then dropped into this calciner, where it undergoes about 90 to 95% calcination. And then this calcined raw meal is then dropped into the far end of the rotary kiln, where it undergoes several reactions to produce cement clinker, which is then finally ground into cement. And then for our application model, the scope of the calciner is it starts at the end of the rotary kiln and then terminates at the start of the preheater stage cyclone system. And then for the conditioning tower, this is located downstream of the top stage preheater stage cyclone, and its main goal is to cool down this hot flue gases to a desired temperature before the gases and the fines are sent to a filtration system such as a bag house and then eventually sent out through the stack. As we can see, the performance of these two units, they depend on the efficiency of gas solid mixing, the heat exchange, the residence time control. Thus, they make excellent candidates for CFD analysis. Calciner, it's a high temperature reactor. It is where most of the calcination happens, and typically about 90 to 95% of the calcination occurs in the calciner. And the key thing that it does is it takes away this load away from the rotary kiln so that the kiln can focus on increasing cement production, making more money for the cement plants, and that also helps sometimes to reduce the kiln fuel demand. And the calciner is not just important from a process standpoint, it is also important from an environmental perspective, because it contributes about 5% of the global CO emissions. And when you include the combustion products, it is actually as high as 8% of the global CO2 emissions. So as you can see, there's a lot of things happening in our calciner. So there's a gas-solid mixing, there's a gas-solid heat exchange, there's some complex reactions, and there's fuel staging and combustion that's happening. So all of this is highly coupled, and it needs it's a coupled CFD software, which brings us to the Barracuda reactor solution. This is a Barracuda users conference, so I won't say why Barracuda is a suitable tool. I'll just say it's a great tool for simulating very large industrial systems like this calciner. And here I have this image. It's a nice cat snapshot of the cement calciner, and I'm only showing the fluid domain here. And the key value to the users is that with this Barracuda model, they can actually visualize what is happening inside the calciner, which is not typically possible with just plant data, which is measured typically at the outlets. So they can look at the reactor flow fields, and with that, they can have a good understanding of their existing operation. And then with that knowledge, they can actually identify root causes of existing issues, such as poor calcination, incomplete combustion, and so on. And the CFD model can also be used as a design tool if they want to evaluate alternative fuels and feasibility of alternative fuels, and also evaluate the decarbonization strategies. Now let's just look at the Barracuda model setup. So the entire setup is primarily derived from this open source literature, the Zhu et al. Paper. So this is open source. You can easily get this paper by doing a Google search. So the model domain, the inputs are all obtained from this literature. Here, I show a schematic for all the inlets. So this calciner is about 64 meters tall, and its maximum diameter is about 8 meters. So it has 4 inlets, narrow inclined inlets for feeding in coal. And then the raw material is actually staged through 4 chutes at 2 different elevations, mainly for good heat transfer. And then we have inlets at the bottom for the kiln exhaust gas to come through. And then we have the preheated tertiary air coming from the cooler. And this is the primary source of oxygen for the combustion reactions. And then we have an outlet where the gases and the particles exit the calciner and then enter the preheated state cyclones. Coming to the boundary conditions and the inputs, so all the flow rates, the compositions, all come from this primary source, but we have supplemented that with other data whenever required. And the raw materials and the coal, these are, and also the sludge waste, which I'll get into it later. So these are modeled as solid species. They have their own PSTs, they have their own compositions, and they can also have their own Bragg models if necessary. And we have included all the major heat transfer mechanisms, such as convection, particle-particle conduction, and radiation. And as Jim pointed out in his presentation, we have a new feature, the thermal wall resistance. Here, we are able to capture the heat loss through the refractory and the calciner shell. And as you can download this application model from our website. Okay, so now let's look at the key reaction pathways. So we have fuel. This can be coal, this can be sludge, RDF, whatnot. And it has some amount of moisture, so that undergoes drying as a first step. So the moisture evaporates. And then we have the devolatilization, where the volatile component of the fuel gets released and leaves along a char residue. And then we have the combustion mechanisms, where the volatile gases that's released as part of the devolatilization, they undergo oxidation, and then the char, which is mainly carbon, also undergoes oxidation. And these two reactions essentially constitute the combustion, and they provide the necessary energy for this highly endothermic reaction, the calcination, where the calcium carbonate from the raw material is decomposed into calcium oxide and CO2. And then we also have the fuel NOx chemistry. We have defined the NOx formation pathways. Both the formation and the reduction mechanisms are included. Now that we have looked at the pathways, now let's look at the kinetic model. So here we have developed a custom kinetic framework. So there's about 10 to, I think, 15 reactions. These are both homogeneous and heterogeneous reactions, and they were developed from open source literature, including the one from Zhu and several other papers, to mainly capture the relevant chemistry mechanisms like the devolatilization, the oxidation of the volatile gases, the emissions reactions. Okay, so the devolatilization, so we are using a lumped approach. What it means is the overall volatile release rate is distributed among key gaseous species such as methane, CO2, hydrogen cyanide, ammonia, and so on. And these key gaseous species, they are estimated by this volatile estimation template. So this is an Excel sheet. This is a utility that we have developed, and it uses mass and energy balance, and it is essentially generates the precise mass fractions of the volatile gases along with the compositions and also the char compositions and the key relevant thermodynamic inputs such as the heat of devolatilization and the heat of formation of volatiles, which can be directly input into Barracuda. So The key utility for users is that they can download this Excel sheet and they can input their own fuel, like for example, sludge, which would have a much different fuel composition compared to coal, and then they can easily generate the volatile gas yields and the char compositions, and they can input into the Barracuda model directly. And they can also assess different scenarios. What happens when you go from coal to sludge waste or solid waste, and what's the impact on the gas production? And then finally, they can also look at the NOx mechanisms, like how much of the NOx, how much of the nitrogen in the fuel goes into hydrogen cyanide or ammonia, which can have a significant impact on the NOx production. So we have the devolatilization reaction, and then the oxidation of the volatile gases. I won't go into each reaction. And this constitute the combustion reaction. And then we have the main calcination. We have the NOx chemistry. Both formation and reduction mechanisms are shown here. Also, we have the CaO, which is acting as a catalyst for one of the reduction mechanisms. Okay, so we have looked at the model setup. We have looked at the kinetic framework. Let's jump into the results section. So whenever we have data, like such as plant data or experimental data or pilot data, we want to validate the Barracuda model, so to build confidence in Barracuda. And we have plant data for two metrics. One is the fluid temperature that you see here on the top graph, and then the degree of calcination on the bottom. So both of these are measured at the outlet, and it comes from the plant data which is available in the paper, and it comes from an actual cement plant in China. And what we can observe here is that, that Barracuda predictions for both the gas temperature and the calcination show very close agreement with the plant data. Like for both the temperature, it's only about 7 Kelvin off, and the raw material calcination is less than 2% off. So this is excellent agreement with the plant data. And what this tells us is that Barracuda is able to capture the coupled gas-solid heat transfer, the heat transfer characteristics, and the overall energy balance based on the strong agreement. And with this validation, hopefully the reaction framework that we have developed with this model can be reused to model similar such models like CFDs or gasification processes with appropriate adjustments reflecting the fuel composition. Hopefully it will be a good starting point for our users to take this kinetic set, make some adjustment, and run with it. Now we'll look into the qualitative aspect of Barracuda's results. So this is where there can be real value, where the users can visualize what's happening inside the calciner. So let me bring it up. Okay, so here, so these two animations, the one on the left, this is the gas temperature. I've created equally spaced slices, and then and I'm visualizing the gas temperature. And this one on the right, it's the oxygen mole fraction. And these two are the instantaneous profiles. And what we can see here is, here we have the tertiary air coming in, and we have the coal injection. So you see some peak temperatures, right? So with this instantaneous profiles, we are able to identify which are the key combustion zones, which are the key temperature hotspots, where is the oxygen being consumed, both axially and radially. We are able to make that analysis. And we can see especially with the gas temperature, you see that there's a spike, there's a lot of combustion happening, and then there's a gradual decrease in the temperature. This is because these hot flue gases are exchanging heat with the colder raw material coming in through the chutes. So there is a drop in the temperature. So overall, the instantaneous profiles can help us to visualize these localized combustion zones and also the mixing profiles. And here on the right, I have the time average profiles. And while this tells us how model is transient, there's a lot of things happening, this interaction of particles with gases. So the time average profiles are very useful because they show an overall stable heat release. and then the oxygen patterns as well. Here we can see that at higher elevations in the calciner, the temperature stabilizes. There is a thermal equilibrium that is established between the gases and the solids. Now we'll again follow the same approach. We'll have the instantaneous profiles on the left, and then we look at the time average profiles. So here we are looking at CO2 profiles on the left, and then the CO mole fractions on the right. And what we see here is, as expected, near the fuel injection zones, we see spikes of high concentrations of CO. This is where the volatile oxidation and the char reactions are most active. So there's some incomplete combustion that's happening, but then you see a progressive depletion of CO as it undergoes complete combustion and then gets oxidized to CO2. With CO2, you have some CO2 coming through the inlet. It gets diluted with the tertiary air, but then it keeps on increasing because there's the reactions that are happening, the combustion reactions, but there's also the calcination reaction, which is producing a lot of CO2. And then the time average profiles are consistent here. It shows a stable CO depletion and the stable CO2 buildup across the elevation of the calciner. Now we'll look into the calcination. This is the main performance metric. This is how they assess the calciner. And these animations, what you see here on the left, these two views, this is the degree of the calcination. And an important thing to note here is the animation itself, it only represents the inline calcination, meaning any pre-calcination that happens upstream of the calciner, like there's some calcination that happens in the preheater state cyclones, that is not included. And the reason for that is we want to visualize how much calcination is happening inside the calciner. And the outlet calcination is just purely based on how much of CaO is flowing out of the calciner. And then this animation on the right, so this is a raw material temperature. And the reason I have it all in the same slide is that we expect as the raw material gets heated up, it will start undergoing calcination. And what we see here is as the raw material enters the calciner, it comes in contact with the hot flue gases, so it starts heating up, and then the calcination is initiated. And then as the particles are going upwards, it starts getting more heat, and then the calcination accelerates. And you see that at higher elevations, it's almost all of the material is calcined. So the lower region is mainly dominated by heating, while the upper regions are dominated by high conversion of the calcium carbonate into CaO, which is the objective of the calciner. Here, my final slide on the calciner. So this is the NOx distribution. And here what you have is, these are all time average profiles. And I'm trying to visualize the spatial distribution of the NOx. So here on the left, there's some amount of NOx that's coming in through the kiln exhaust gas. And again, you see spikes of NOx being formed. And this coincides with the peak temperatures that we saw earlier, and also the oxygen, consistent with the oxygen patterns. And then this cross-section contours essentially shows the spatial balance that exists between both the NOx formation and the reduction mechanisms, because as you see higher up in the calciner, the NOx is actually being reduced because there is a reaction for the NOx reduction where the CaO is acting as the catalyst. So this is consistent with the calcination that we saw in the previous slide, that the NOx is getting reduced at higher elevations. So overall, the key takeaway here is that instead of getting one data point at the outlet, it's usually what the plant data is about. They have one NOx value. Here, the plant operators are able to visualize the spatial distribution of NOx inside the calciner. Okay, so I do have one more slide, sorry. So now that we have we have developed the baseline model framework with coal only. We want to extend it. We want to see how it can be utilized. And here, this kinetic framework has been extended to study this co-firing scenario. Here, 20% of the fuel of coal has been substituted with municipal sludge. So we have a sludge coming in. This is the thermal decomposition furnace. So sludge is coming in. So we have some preheated air coming from the top. So sludge has about 45% moisture. So the main idea here is the sludge gets dried out in this furnace before it enters the calciner. And going back to the volatile estimation template, because the sludge has a different composition, I'm able to use this template to directly generate this volatile gas composition, the char composition, the thermodynamic inputs, and directly input it into Barracuda and then run the model. So it was as easy as maybe an hours of time before I can start running this model. And just like previous qualitative analysis, we can do the same. We have provided the post-processing template, so you can easily recreate the same results. So this one shows the CO2 mole fractions, the oxygen mole fractions, and then finally this is the gas temperature. Okay, so now we are done with the calciner. So we'll, okay, still have some time. So here, so we'll look at the second application model. So this is the cement conditioning tower. Here, we are not looking at combustion. So here, the main idea is to simulate the evaporative gas cooling, essentially cool down the hot flue gases before it reaches the end of the conditioning tower. This schematic you see here, this is the CFD model. So we have gases and raw material coming in. This is the hot flue gases. So the raw material gets separated out by in the cyclone, and it's collected at the bottom. And the hot flue gases with the entrained fines enter the gas conditioning tower, where we have defined some injection nozzles. So we're not actually modeling the nozzles, but it's modeled as point source injections. So it has a specified water flow rate and atomizing air, and that will cool down these gases to some desired temperature. So overall, the key value here is users are able to do optimization with the water nozzles. How many nozzles do you need? How much quantity of water? Where to put it? Because the key goal here is to achieve 100% evaporation within the minimum possible height. Because any moisture that's still present will mess up the downstream filtration and will be very expensive for the cement plants. Okay, so here we are looking some qualitative results. So we are looking at gas temperature in the first two frames, and then we are looking at the steam mole fractions. Here, the key idea is, so gas is coming, hot flue gases are coming in about 450 degrees Celsius here. There's water nozzles, so that's taking away heat from the gases, and the gases are getting cooled to about 250 degrees Celsius. And here, what we can see is that it's not completely uniform, the gas temperatures. The reason for that is the gases that are coming out of the cyclone have a strong swirl component to it. And usually there's some flow straighteners that's included, that's usually installed to minimize this effect. But again, this being an application model, we are not doing it. So that swirl significantly affects the trajectory of the droplets, and you see some water impinging on the walls. But the key takeaway here is Barracuda is able to show the gas cooling, and then it's also reflected by the mole fraction of the steam contours here. Okay, so here this slide I'm trying to quantify the evaporation. And to do that, what I have is, so the schematic on the very right, I've created equally spaced flux planes. So one corresponding to the elevation of the water nozzles, and then I have like 6 equally spaced planes. And the goal is to assess the evaporation. How long does it take for 100% of the water to evaporate. And from a temperature standpoint, we can easily see that the gases coming in at about 450 are very quickly cooled to about 250 degrees Celsius. And that's what you see here. You see like there's some variation between the plane 1 and plane 2, but then from plane 2 to plane 5, the temperature has stabilized. And then the graph on the top here, this shows the evaporation versus time. We see that 99% of the water has essentially evaporated, like 11 meters below the injection plane, and nearly all of the water has evaporated by the time it exits the conditioning tower, which would be the objective of the cement plant. They want no water leaving the conditioning tower. Okay, with that, I'm at the end of my presentation. Yeah, as Shashank mentioned, please download these application models, try it out, modify it, and I'm happy to take any questions.